uh, give a warm welcome to Dr. Daniel Puzzuoli, please.
Thanks. Yeah, thank you very much for having me. Um, just one question. Can you see my mouse like over the slides or
Yes,
no? Yes,
yes,
okay.
I
Yes,
can see.
yes.
Okay. Okay. So, second. Okay, yeah. So I have this talk broken into two pieces. The first one is kind of just since this is a lecture series, it's kind of like what I would say to somebody just starting to get into the field, a quick summary of some things. So it's just like an intro to numerical quantum optimal control. So I'll talk about what it is exactly, what are the ingredients. I'll talk about some classic algorithms that if you Google this, you'll immediately see. I'll talk about one technical thing, which is setting up pulse parameterizations, which I find is something that is, I don't know, I guess confusing or to some people. I just wanted to say the type of thing that we do. And then I'm going to talk about some advanced numerical methods, just briefly, for how we build robustness into the optimizations. And then the second part will be kind of like a shift to like a research talk on some work that we've done recently. And it's like the title of this talk, so it's on some work with calibrating numerically optimized pulses. So that's kind of like a second piece of this. Um, yeah. So what is quantum optimal control? So when people say this, or they'll say optimal control theory, or there's a lot of different sort of versions of this. I'll often say numerical control. So it's basically using classical simulation and optimization to optimize controls for quantum systems. So, for example, designing pulse shapes to implement a gate. So here is a picture of a pulse. So these are the types of shapes that we optimize. And these are like, I'm not a device physicist, so I have a very simple description of these things, but it's like we have here's a picture of an old IBM device and there's qubits on there, and we send these signals down and they interact with the qubits and generate sort of evolution. And that's how we implement the gates. And just one really quick comment is that some people don't like calling sort of the numerical optimization of things optimal control, because the term optimal control theory is already a name for a theoretical mathematical field. And it's more about proving things and not about applied numerical work. But this is how it's used in the quantum literature, at least for this stuff. People call it optimal control theory or OCT. So I think that the name has stuck already, but just the point that I wanted to say. So what are the ingredients? So when you're doing an optimization, or what do I mean when I say doing numerical optimization? So these are sort of the pieces that I'm talking about. So you start out with a model. So you have some model of your system, say it's a transmon or some spins or whatever, and that'll be described. So here's in terms of the unitary version of the Schrodinger equation. So you can have the Schrodinger equation or like the Lindblad equation or maybe some other master equation. So you start with a model. This is how you think of your system. And then you have some task that you want to do. So implement a gate or do state transfer or something like that. And so starting with your model, you define what are the things I actually want to do with that, and you encode that into some quality metrics. So like fidelity, gate fidelity, say maybe you want to minimize leakage at the end of the gate, or you want this thing to be robust. And then once you've got your model and you've quantified how you want to, or what you want to do with it, you then want to define a pulse parameterization. So you're saying, okay, I'm going to want to optimize a control sequence, and this is to do whatever is encoded in my quality metrics. And well, then you need to parameterize control sequences to be able to do an optimization. So you need some way of mapping parameters to basically control shapes, and that's going to control how you explore the space of controls. And so these are the kind of the main pieces, and this defines your objective function. So your objective function will take your parameters as input, generate the shape, solve the model using that shape, um, and then compute quality metrics and output that. And then you'll, of course, plug this into some classical optimizer. And this could be gradient based generally. I know people use non-gradient based methods as well. In my experience, to explore the space sort of efficiently, it's like really important to have gradients. So having gradients is a really important thing. So not only computing this function, but um, having gradients of this function as well. And just so my rough perspective on this field is as follows. So first of all, I'm going to be giving some talking about a couple topics here to introduce the topic, but this is a huge field. There's stuff coming out about this all the time. So this is really like a really small slice of things. So there's tons of stuff out there, lots of research, lots of packages to do these things. So I'm obviously not going to talk about the vast majority of things, but just yeah. So there's a ton of stuff out there. And yeah, one point I want to make is that this body of work is primarily focused on sort of technical numerical aspects of the problem. So things like I said, computing derivatives is really important. So computing derivatives is just sort of a technical issue um, that's really important. So there's a lot of work in that. Um, Things like even how to parameterize the pulses. So choosing the pulse parameterization, that controls how you explore the space of controls. So that's important, obviously. Um, so like there are papers that literally like say, here's a parameterization. Um, And then there's also things just like how to compute certain non-trivial metrics like robustness. There's of course, the solvers, but that's sort of classic ODE stuff. Um, and so my general view is so all of this work is great, and I do stuff in here too. But my general view is that more work needs to be spent on um, how to reliably and efficiently translate these things to experiment. So we have like there's a whole body of literature on doing these optimizations and stuff like that. Um, in the numerical aspects of it. But there's not as much work in actually applying these things to experiment, and definitely not much work sort of trying to take an algorithmic view to how to apply these things to experiment um, efficiently. So I mean, there is work on that stuff, which we'll talk about, but it's really not that much compared to the sort of overall body of work dealing with the numerical aspects. And another thing that I'll say is, so people call a lot of the things out there control algorithms, but they really are kind of technical numerical pieces. So like I would want to use the phrase control algorithm to be like a holistic thing that includes the optimization as well as the application to experiment and the methods for doing that. Um, so yeah, that's just a very minor point, but yeah. So I wanted to talk about some well-known things. So these are the things that you would, if you Googled quantum optimal control, you would probably find these things. So the first is like the most classic paper on this topic, and it introduces this algorithm, gradient ascent pulse engineering, which for short people call it GRAPE, or they introduced this acronym. Um, and basically, what this paper shows is if you parameterize your pulse as piecewise constant, and so the parameters you're going to be optimizing are just the amplitudes of these pieces, they show a way to nicely compute the derivatives of the final unitary um, with respect to these parameters. So I'm not aware of stuff before this, but that was a really early paper, and it's kind of like the thing that gets cited all the time. Then another one, this is much later, but I see it cited a lot these days, is gradient optimization of analytic controls, and they've acronymed this as GOAT. And this is again another way of just computing derivatives. So they show how to compute solution derivatives for arbitrary parameterizations. So that's nice. This, if you're aware of this terminology, is basically like a forward mode differentiation or automatic differentiation type algorithm. So yeah, so here we had piecewise constant. This paper they show, okay, you can compute derivatives for arbitrary shapes. Um, and then another paper that gets cited a lot is this, it's called chopped random basis or CRAB, which I think was, I don't know if it was like introducing these two papers simultaneously, or I think these were like related papers. And this really is just like a suggestion of a pulse parameterization that they think is good for exploring the space. And so they advocate for a decomposition rather than piecewise constant. for something else, a decomposition in terms of like sines and cosines. So like a Fourier type decomposition. Um, so yeah, I primarily mention these. I mean, these are kind of like classic things, and I see them cited all the time. So I wanted to just say these. Um, One thing I'll say is I wanted to say is that this issue of computing derivatives um, today is kind of not a huge deal because we have automatic differentiation. Um, and so many modern packages support automatic differentiation. So I'm just listing Python ones here because that's what I'm most familiar with. But there's automatic differentiation in most languages, as far as I'm aware, or think like packages that enable this. So TensorFlow, PyTorch, JAX are the main ones I am aware of in Python. Um, and I say in quotes that basically having automatic differentiation essentially solves the technical issue of computing derivatives. So this is some simple code in JAX. So you can take a function. So this is like a pseudocode thing. So say it takes in your parameter input parameters and will output some objective value. If I write this function, I can just immediately, using this JAX grad transformation, I can get a function that computes the derivative. Um, and what this means is that you can go ahead and define arbitrary parameterizations, you can define arbitrary objective functions, and you can still differentiate. Sorry, arbitrary, like they have to be differentiable and recognized as differentiable by the package you're using for the automatic differentiation, but that's a pretty broad category. Um, yeah, so yeah, I just wanted to make this point. Like, so if you are getting started in this field, um, you'll hear about grape or goat or things like that. And I think there's still value in like sort of customized differentiation routines because, these things will use very general differentiation, they're automatic differentiation algorithms. But yeah, it's like, it just makes things so much easier to use automatic differentiation because then you can basically write whatever you want that's compatible with autodiff and it'll it'll work. You don't have to write these custom things for like every new objective function you want and stuff like that. Okay. So one thing I wanted to also say is a way that we like to build parameterizations ourselves when we're doing the work, like the type of stuff that I'm going to talk about in the research portion. And this is kind of just a standalone slide, but just again, if somebody was, say, an intern was coming to work with us, I would show them how to do this. And this is, I'm going to be describing a recipe that we use internally and is described in this paper, but this isn't like novel or anything. But it's just, I have some nice images from this paper already and it's described there. So in more detail. So if you're interested, you can look there. Um, so basically what our parameterization is, or that we like to use, is a recipe for defining an envelope function with, you start out with some given number of parameters that you want to use, so n, and we say, we want to parameterize controls that are bounded between, let's say, -1 and 1. Typically, this could be any interval, but you have some bound, you want them to live within some range, and you want them to have, let's say, arbitrary smoothness, like you have some smoothness level that you want them to satisfy. And here, I'll explain it in a second how we get that, but basically, uh, that'll be defined by how you sort of convolve it later with something. But yeah, so okay, so what this function is that generates these smooth pulses. So the parameters P are going to be these input parameters. And so what you have to do is just choose some basis of piecewise constant things. So because we're doing everything with arrays, so you just choose some basis. Um, Typically, we choose like a discretized Chebyshev basis. So we'll have some interval and we'll decide how finely we want to discretize that. You can discretize it as much as you want. And then you just choose, say, like n basis elements from some basis. And here we're doing real and complex. So you either split n into two or have it be 2n or something. But so you do that, and then your parameters just become the coefficients in a linear combination of this basis. So in this case, that's what this first image is. So we take a linear combination. You can see it's not bounded. It goes up to these 10 and -10 values. And also, the parameters we're going to be doing we typically do unconstrained optimization. So the parameters can take any value. So this really can be arbitrarily large, basically, in terms of amplitude at this point. But then we enforce the bounding next by passing every sample through a differentiable mapping that takes all of the real numbers into whatever interval you want. So for example, here we use the arctan, normalized arctan. Um, and yeah, basically the only thing is it needs to map it into this interval and be differentiable so that it can be automatically differentiated. Um, so that gives you the bounding, but this thing can, like this one's not too jagged, but it can produce really jagged things. Like if your parameters have really large values, arctan will like really squeeze things and it squeezes them non-linearly. So you can, so like here you see there is a jump and you can start getting some crazy jumps here. And then finally we convolve this thing with a kernel that has unit area. So just a typical discrete convolution. Um, and it kind of smoothens it out. And you can have an even finer discretization for that. So that's what we do here. And so long as it has unit area, it'll preserve the normalization. Here, because the interval is like symmetric about zero, that's fine. If it wasn't, maybe you'd have to do something like shift the interval around to make sure that this preserves everything. But yeah, that's the idea. Yeah, just a little technical thing, but again, something that I would explain to somebody who's just getting into things. One final thing I wanted to mention, which is another sort of key thing, is optimizing robustness. And if you look in the literature for optimal control, you'll see there's different schemes for doing this. I'm going to mention a couple of them, but this again is just like a general thing that people should be aware of if they're interested in this stuff. And here I'm just going to show a couple slides, and it's going to be very cartoony and high level, but just to draw attention. Um, So yeah, so model uncertainty poses a challenge to numerical optimization. What I mean by that is, say you think you have your model is some Hamiltonian H0, but in reality, when you go to a device, um, it's maybe there's some other component in your Hamiltonian, and you could parameterize this in lots of different ways. But say in a really simple case, it's like some epsilon times some other Hamiltonian, so it's a slight deviation. So if you just straight up optimize a pulse for H0, it may not work for this deviated Hamiltonian. Um, Especially, sometimes you do these optimizations and they'll really utilize really fine aspects of the Hamiltonian. And if you start changing the Hamiltonian, it'll totally mess up your trajectory through, say, like unitary space if you're doing a gate. And so in practice, like even for, simple drag pulses, the uncertainties in the model are kind of handled with calibration. So rather than characterize further, it's like, okay, we'll just calibrate. We don't need to know exactly what the model is, or we don't need to know it better. So we'll just calibrate. But sometimes you want your pulse to be actually robust. So we want it to work for, say, a range of epsilons, or have some, quality above a certain threshold for a whole range of epsilons. And so one approach to adding this into optimizations is to use distributions or adding distributions to objective functions. To say this was like your original objective function G, which we'll now write as a function of epsilon, and P are your parameters. So it's like, what's your quality for a certain value of epsilon? And then you define a higher level objective that's just the weighted average of this quality metric over different values of epsilon. So that's a really simple thing you can do. But another approach, which I want to talk about because we use it in our research, so I just want to give some context for that, is perturbative robustness. So perturbative robustness, rather than using distributions, it's kind of like a pseudo-analytic thing. I mean, it's still fully numeric when we do the calculations, but it's based on perturbative expansions. So perturbative robustness looks at expansions of the operator, of the operation, say the unitary and the uncertainty parameter epsilon. So we take, say, our unitary, which we write as a function of t and epsilon, and expand it out as a power series in epsilon. And this would be kind of like the Dyson series, and then you could also do the same thing for the Magnus expansion. If people are familiar with that, that's another thing you'll see if you look into this stuff. Um, and then, okay, so you have this expansion, and then what it means to add perturbative robustness. There's different things, but the simplest version would be um, adding a term, like say, take the first order correction and just defining a term that's the norm of that and trying to minimize that. So it's like basically we want it to be first order insensitive to epsilon or something like that. So that would be kind of like the way of thinking about it. And then you can go to higher orders if you want. So yeah, just compute these expansion terms. And sorry, so big T here would be like the time of the gate, the final time of the gate. So you would compute these expansion terms and just add to your objective function something that tries to minimize the impact of these. Maybe it's the norm. We often subtract, say, like the identity component if our Hamiltonian is not traceless. So there's little finicky things here, but that's the idea. And so this idea is common in control theory. So it's basically like looking at derivatives of the unitary with respect to epsilon, and this is called sensitivity analysis. But in quantum, this goes way back to like the beginning of quantum control, um, and it originates from NMR. So if you've heard of like dynamical decoupling sequences, um, which are still used today, and like have that theory has like advanced quite a bit, but this goes back to NMR. And so this paper details sort of the perturbative analysis explanation for why a lot of the control sequences they were using were working. And so this idea they used that there in that field, and then so like lots of control sequences were developed in NMR back in the day using this idea. So there's a ton of numerical algorithms. So like the problem now for doing numerical stuff is then actually computing these things or computing things related to these expansions. Um, so there's way too many to list. I just want to mention a couple. So the one that you'd probably see the most often is this filter function formalism, and this is what's used by Q control. Um, so here's one of the many papers talking about how to compute these things. Um, so you'll see that. So they don't exactly compute this, but they do a perturbative expansion and then collect terms and compute something related to this. So that's used there. And then this is a paper that we did this year, which I referenced in that previous slide. But so this is built into Qiskit dynamics. It's some algorithms for computing these expansion terms in a multivariable setting for both Dyson and Magnus. So that this work is kind of like directly computing these expansions. And there's other stuff too, but again, this is one of those things that's pretty expansive, so it's hard to cite everybody. Um, okay, so that's that. So again, so the beginning is just kind of a here's some random things that I would like have in a first conversation to somebody, say like an intern at IBM. Now I'm going to get into the second half of the talk, which is this research project on calibrating numerically optimized gates. So this is work done with some collaborators at IBM, so Holger Haas and Ken Wei. And this work was done over the last couple summers with some interns. So this past summer, Emma worked with us, and then the previous summer, Vivek and Zoe worked with us, and they were really, really awesome interns. And so there isn't a paper out on this yet, but it's very close to being finished, so it'll be released in the next month or two, hopefully, or on the archive, I should say. Okay, so let's start out with some motivation for this work. And I've mentioned some of this stuff. Okay. Yeah, so I gave this a talk on these slides to a group of people doing numerical optimal control. So everybody likes that stuff in that talk. But so the idea is the motivation is the model-based numerical gate design has a lot of potential, and the reason is it can enable flexible and automated design of gates with nice properties for arbitrary systems. So that's really like why we do this stuff at a very high level. You give me an arbitrary Hamiltonian, I can just start running optimizations and potentially build lots of crazy things into these pulses. And that's potentially really awesome. But the issue is that experimental application is challenging. And in general, when I've seen it hasn't been like it seems kind of like an art form at this point. So that's sad face. And the issue is things like model uncertainty, which I mentioned. And in principle, you can build things to be robust, but you can't build things to be robust to everything. And there are things that you don't know that are going on. So it's basically impossible to build something that's perfectly robust to everything. Um, so in principle, you would say, okay, well, then we'll just still always have to do some calibration. But the problem is that calibration is also hard in this context. And the reason is that when you do these numerical optimizations, you typically have high dimensional parameterizations, um, which basically already just makes things hard. So you have a huge dimensional space that you need to search through, and you're trying to do it on your real device, which maybe you have limited time on, or it takes time to collect data and it's noisy data. So searching through this space is really hard and becomes kind of prohibitively slow. And part of this is that there's no clear correspondence between parameters and, say, experimental data. So, like with drag, for example, simple Gaussian pulses or drag pulses or something, there's going to be a simple correspondence between, the overall amplitude and the rotation angle. But in general, this isn't going to be true. So if you have some arbitrary parameterization, there's not necessarily a clear link between these things. And this problem gets even worse if you think about applying this to a huge device with many qubits. Um, so sometimes people say, okay, well, you can sort of alleviate this issue by characterizing things further, but we don't actually want to spend the time and resources to do deep characterization of every qubit. Maybe even for 100, it could be possible, but when you start talking about thousands or millions, like that's not going to be possible. Um, or at least I don't think it'll be possible, but maybe it could be. And furthermore, it's going to be infeasible to optimize a gate for every qubit. Um, do like a unique optimization for every qubit. So there's going to need to be some way of generating sort of initial inputs to calibrations that's more efficient than running a full from scratch optimization. So what we really need if we want to apply these techniques realistically in a way that can be used on large devices, um, is scalable workflows, both for, I say, control discovery and optimization. So that's like coming up with the shapes you want to use. And then also for the calibration processes. So once we think we have a shape we want to use on one of the qubits, we need to be able to efficiently calibrate it and deal with this high dimensional shape issue. And so this talk is focused on this part of it. So we're going to start from the assumption that, okay, say we've run an optimization, say we're even just looking at one qubit. How do I nicely calibrate a pulse on that qubit? And not only that, but we want it to be as simple as possible. So we want to be able to find, in quotes, simple calibration process for numerically designed gates. And the standard that we're going to use for measuring simplicity is things like how we calibrate, say, like drag pulses, which is like insanely simple, relatively speaking. So drag, when we calibrate these things, I'm not sure exactly how many parameters we use. Maybe it's like two or three, like the overall amplitude and the amplitude of the drag piece. Um, but yeah, there's a very small number of parameters. There's a direct correspondence between how you want to tune the parameters in the experiments. Very simple. And the question is, can we achieve something even like approaching this level of simplicity for if I do some optimization and I have a ton of parameters, um, how can I approach this level of simplicity for tuning up this pulse? And so this slide just collects some prior work that have broken up into various categories. So one is what I'll call black box optimization, and all I mean here is you just take a standard optimizer and apply it to the experimental data. Um, so there's a couple papers here that do that. They use the CMA-ES optimization algorithm, but I think so these are nice algorithms, but they're still exploring very high dimensional spaces here. Um, what they do in this paper is they take this approach, but also they run an optimization and then use that as the initial guess for the experimental optimizer. Um, Another thing category is what I'm calling gray box optimization. So this is applying things like reinforcement learning to experiments, um, to design pulses within experiment. And I call it gray box because it's like sort of a classical optimization process, but there's some knowledge of the structure of the problem. So they go like step by step and find uh, the next value of, say, a piecewise constant pulse that they want to do. This one is cool, where they try to combine model and experimental data. So this paper, I think it was called D-Grape, um, but they try to like basically get an effective gradient to do searches in experiment. What they do is they take experimental data and still keep using the model in the calibration process to sort of come up with directions to move in the calibration in the experiment. Um, so that's cool. Another thing I put in here is just standard calibration fits into this category too, in the sense that the way we calibrate, say, a, a Gaussian drag pulse assumes something about the model. So like again, this connection between amplitude and rotation angle is used in the calibration scheme. So like the model information is still being used. And that's in contrast to say like these, where there's really no model present at all, aside from what the optimizer sort of starts figuring out about the problem in terms of how it searches the space. And then another one, which is kind of the flavor of what I'm going to talk about, but it's not really like formalizing the problem and not doing it in a general way, but still kind of gets at what we're looking for. Um, is this paper by QControl? And so what they did in this paper is they don't fully explain, if I remember correctly, how they then did the calibration, but they optimize a pulse shape, and they don't fully explain where the pulse shape comes from either. But once they've done that, they then, when they're doing their calibration, all they do is they tune the relative amplitudes, or sorry, the overall amplitude and the relative amplitude between the real and complex parts of their pulse. So however they did the optimization initially, when they do the calibration, there's two parameters to calibrate. So that's cool and kind of the vibe that we're interested in. But what we're interested in is a bit more general than this. So, maybe this works for qubits, and maybe it works for this particular class of pulse shapes, but we're really wanting something that's of the flavor of, typical numerical control, which is we optimize something we can have a fully general parameterization, fully general Hamiltonian, do the optimization. And then the question is like kind of what is the analog of this in a fully general setting? Okay, so for the rest of the talk, this is what I'll talk about. So I'll talk about the main idea that we have, which is pulse parameterization, dimensionality reduction. So I'll formalize the problem and talk about the method. And then I'll talk about two experimental applications that we applied this to. So for frequency and amplitude robust single qubit gates, and then another one for removing spectator errors in single qubit gates. And then I'll just conclude with some outlook. Okay, so the dimensionality reduction problem. So this is the setup. So this is similar to that slide on the ingredients part, but I'm not looking at objectives here. I'm just thinking about start with a point in unitary space, a point in parameter space. I have my parameterization, could be high dimensional. Of course, I have my model, and these things, my parameterization plus my model, basically defines a mapping from parameter space to unitary space. So given a point in parameter space, construct a waveform, simulate model, get a point in unitary space. And the question is, say I run an optimization, and I find a point P0, say in parameter space that does the things that I want. The question is, how do I find a smaller dimensional parameterization that I can then use that'll be good for experimental tune-up? And another way of phrasing this, so given an arbitrary mapping, so I have a function from Rn, the parameter space, to unitaries of some dimension, and some point P0 in this parameter space, what are good directions in parameter space for experimental tune-up? And the question is like, what are the good directions for kind of like moving around locally in unitary space? So the idea is really simple, and it's to look at the Jacobian of this mapping from parameters to unitaries. So basically linearly approximate this mapping. So again, say I find P0 from optimization, and I think my model's like pretty good, but obviously it'll still need some tweaking. Um, so here's my unitary at P0, and then it's got a linear correction of the Jacobian of this mapping at P0 times my deviation in the parameter space. And then what we do is we look at this Jacobian, take a singular value decomposition, and then the right singular vectors, sorry, there's a notational mismatch here. This is V and this is U, but these are supposed to be the same. The right singular vectors are orthogonal directions in parameter space, and the left singular values or vectors, excuse me, are points in the unitary space. And basically what these say are kind of like what are the most, maybe that's my point here. Yeah, so the SVD kind of gives you the most significant directions in parameter space for moving through the unitary space locally at this point, P0. And the idea is, okay, this is our starting point, and we'll use these directions for calibration. For single qubit gates, we just take all of them because there's only three. But in general, for higher dimensional things, maybe you would need to choose them more carefully. But for here, all we're talking about is single qubit gates. So pretty straightforward. Take the derivative and then see, based on that information using the SVD, what does it look like the best local directions are for tuning up the unitary at the end. And this kind of assumes that you're already close. So it assumes that your model is good enough somehow to get you close to what you want in the unitary space. It's hard to quantify exactly what that means. But we tried these things out in an experiment and it seems to be working so far. Okay, so 2 experimental applications. I'll talk about 2. So we applied the same workflow to 2 optimizations. So one was gates robust to frequency and amplitude variation, so single qubit, and another is gates robust to spectator interactions. And so, yeah, we use the same workflow for both, but I'll walk through it in more detail in number 1. So there's 3 steps: optimize the gates numerically, do this dimensionality reduction, and then calibrate. Okay, so application 1, again, the task here is to design a single qubit X pulse that is or X gate, I should say, or a pulse to do an X gate that is robust to frequency and drive amplitude variations. So to do this, those ingredients that I was talking about, we need to build these things. So we pick up parameterization. We have our model, and here we use that recipe for building a parameterization that we talked about earlier. And I think we used about 50 parameters. And then for objective functions, we use, so this is an infidelity term. So I'm just showing these things. Infidelity term, this is a leakage penalty. So starting out in the computational subspace, this is like a projection operator. Penalizing mapping outside of that. The infidelity technically captures this, but we like to sort of penalize it extra basically, so that if there is error in the gate, it's not going to be leakage, because leakage is considered to be, kind of like the worst form of error. And then these are these robustness things. So derivatives of the unitary with respect to these other parameters, frequency and amplitude robustness. And then we linearize these into a single objective. So we have weights and stuff here, but just as a cartoon of what our objective is, this is the idea. And then we run an optimization, so gradient based using BFGS algorithm in SciPy, and all the gradients are computed with automatic differentiation. So this simulation and computation of these perturbative terms, that's all done with Qiskit dynamics, which is works with JAX. Okay, and then step 2 is to do this dimensionality reduction. So we've run our optimization at this point using what I showed on the previous slide. And then we found this point P0 that has all the properties we want. And now we do the dimensionality reduction, and this is what we get. So this was the pulse that was optimized. And then these are the directions um, to what's it called? To tune up in that the thing spits out. So these are some orthogonal directions. When these get added to this, because our parameterization is nonlinear, the shapes won't exactly look like this, but these are the shapes fed through our parameterization at zero. Yeah, so we calibrate in these three directions, and then the final step is to calibrate. So to calibrate now, you need to choose error amplification sequences. Um, so these are the sequences that were used. So it's basically a repetition sequence of our gate, but then with some Z rotation. And in IBM devices, this is done virtually. So it's just a changing phase. And I forget exactly what values are used here. But yeah, so this is very similar to what's used for drag pulses, but just with more phase values. And so here, something that's kind of funny about this is that then the interns, as well as Holger, one of my collaborators, then just tune these things up by hand um, by looking at the experimental data and tuning up in these directions. And this is he just did it by hand because we wanted a proof of concept before automating these things. But it's actually kind of promising that this worked. Like it was actually feasible for him to do this by hand, even going through the IBM queue and everything. I think it takes like a couple hours or something. But like I can't remember what the number of evaluations is of these things, but they're not. It's like the same order of magnitude as a drag thing. So it requires more because there's more experiments, but it's in terms of efficiency of device usage, it's sort of like a reasonable amount of increase in complexity. And we'll talk about the quantification of this in the paper, but I don't actually remember off the top of my head because I didn't do these calibrations myself. And one thing to note is that the calibrated pulse is essentially identical to the uncalibrated one. So I'm just showing it again here, but there's no point in showing the difference basically because they look exactly the same. And this is good because that means robustness properties are preserved, hopefully, but it seems like they are. And it really sort of our assumptions that our model is pretty good and we're just kind of like tweaking the final unitary is, sort of validated in this, at least experimentally. Okay. So just to show some experimental data, so the top is for drag and the bottom is for our pulse that we optimized here. And all we're doing here is starting out with the qubit in the ground state. We're applying the pulse once, but sweeping on the x-axis amplitude here on this plot and frequency of the carrier frequency on this plot. So if you see here for drag, sorry, and we're plotting the population in the excited state. So we see like basically as we shift the amplitude away from what we thought it was, how robust is this in terms of being able to invert the state, both to amplitude and to frequency. So drag is not robust basically. So you see kind of the shape where around where we thought it was, or maybe it's actually a little bit off, but there's a point at which it peaks and then it kind of drops off. Similarly with frequency. But for this pulse, you see this stays quite flat. And similarly, the frequency stays flat here. So this is kind of validating that it is robust to these things. And yeah, so flat. Yeah, I forgot about that. Okay, now in terms of RB data, so what is the actual fidelity of these things? So this is the optimized pulse. This is drag, and you can see the fidelity is a bit worse for ours. But it's only because, actually, I should have mentioned this on the previous slide, but our pulse is 2 times longer. So to build in these properties, we could probably go shorter, but as a proof of concept, this was where we got in terms of pulse length. But yeah, so the pulse is longer, and it turns out both of these are coherence limited. So this is really cool, again, as like sort of a more theory math person working in this field. I've been talking to experimentalists, and there's always this question of, well, how do we calibrate these things? How do we calibrate these things? And being able to get it coherence limited, essentially on our first try was with this method was awesome. I'm really happy about this. Okay, I guess yeah, maybe I should hurry up. I'm running out of time, but I'll just say this last application. So this one's a bit more involved, but I'll skip a lot of the details. So the next one is spectator errors. And I'll explain what that is. So looking at CR devices, basically the coupling is always on. So if we have a 2-qubit Hamiltonian, this is like a really simple way of writing it. Um, so I have my sort of single qubit term for qubit 0, single qubit term for qubit 1, and then there's a coupling. This coupling is always on. And here I'm talking about 2 qubits, like actual things that we want to use for computation, but can also be true. And this is part of why it's called spectator, for just like other systems that are floating around, that your qubits might be coupling to. So they'll just be coupled in at all times. And so, yeah, so this is a kind of technical point, but when we do our computations, or when we think about what the computational states are, these are actually what are called the dress spaces. So we look at the eigenvectors of the static part of this Hamiltonian, so not including these drive terms. And those will actually be the computational states. So if we look at, say, x0, um, if you move from this sort of standard basis that we write things into the dress basis, um, x0 actually becomes a non-local operator. So it looks like x tensor identity, which is kind of what we think of it as. But then you also get this x tensor z, z tensor x, and I tensor x contribution. And this is in the computational subspace. Um, so of course, it's close to x tensor identity. A is going to be close to 1, and B, C, D, these coefficients are going to be close to 0, but they're not 0. And this isn't exactly 1. So this term exists. And in fact, CR gates are based on this. So these terms, they're not super strong, but they are there and they are significant enough to define 2-qubit gates, or to utilize for 2-qubit gates. But this is kind of like for single qubit gates, this is kind of crazy because it's like, okay, I'm driving 1 qubit and really I'm enacting a non-local operation on everything that it's coupled to. It's small, of course, and potentially off resonant, but it still exists. Yeah, okay, so that's that point. And so actually there was a paper that was posted in the archive earlier this year by people at IBM. So this is one of the people that's working on this project as well, Ken, um, where they show how to detect these things. So they're looking at a pi/2 pulse here, and they had 2 qubits on this one device, and they set up this control sequence. I won't go into the details, but basically it's another just amplification sequence for a pi/2 pulse. And all they're doing is interacting with this 1 qubit or driving this 1 qubit. And this pulse sequence is set up so that ideally everything should be in the ground state at the end. And obviously the other qubit, you're doing nothing to it. So that should definitely be in the ground state. But as you sweep the phase here, you get these lines. And the y-axis is the number of repetitions of this block. You see these lines start to appear. So this is the driven qubit, I believe, or maybe it's the other way around. But one of them is the driven qubit, and one of them is the spectator in this case. So you see that there are these kind of spikes where you're sort of effectively with this repetition sequence, like going on resonance with these interactions. So it's a small effect, but it's there for sure. So what we wanted to do is design a pulse to get rid of this effect. And basically what we did was we applied those perturbation methods that I talked about earlier to get rid of these terms in the optimization. And so here we ended up running new experiments on different qubits just because I think the properties had changed since the time of that paper. But here's like the up-to-date data that we actually got from the qubits we worked with. So this is for the drag pulse. This is the exact same plot, but just for another pair. So you see these lines that appear. It's driven on this side, spectator on this side. This is our optimized pulse, which is kind of funky looking. But again, it was optimized to perturbatively remove these coupling terms. And you can see that these lines go away. This data was a bit noisier for some reason, which is something that we're figuring out. But definitely on the spectator, it's nice and clean, and that line is gone, and there's no clear line here. So this is pretty cool. This was also, I have a point here. Yeah, so we also optimized this to be coherence limited. And the cool thing with this pulse, so it's not robust to amplitude and frequency variations, but it is the same length as the drag pulse. So we're able to get this property in the same amount of time as the drag pulse. In this case, they had basically the same fidelity, and it's because this effect, um, while it does contribute to the fidelity of the operation, it's still kind of below the coherence limit at this length. Um, so one thing we'd like to do is optimize a shorter pulse as well. So go into a regime where that will actually be kind of like a leading, maybe not leading, but like at some point where there's like it is like a dominant source of error beyond what you're limited to by coherence, and try to remove these effects. The challenge there is that then you have to start driving with higher and higher amplitudes. So then more other issues start appearing. So there's those challenges. One thing to note here is that this is like 3 times higher amplitude than this as well. And we're still able to sort of get a high fidelity pulse, and its coherence limited. So that's cool. Okay, so that's that. Again, the paper will be coming out soon on the archive. So just to summarize, we're developing a workflow with the goal being to be able to calibrate these pulses, and it's based on this dimensionality reduction technique. We need to automate this. Oh yeah, I didn't say it, but by hand, they had done iterated line searches on each parameter. So this is like a very, extremely simple optimization procedure, which is cool. Obviously, applying this to 2-qubit gates would be a nice thing to do. With the automation, I think, yeah, the goal is to, okay, proof of concept for single qubit. Now let's try to do it for maybe still a single qubit gates, but for a whole device. That'd be nice. Um, okay, so we have also here, we presented one idea for how to do this reparameterization. It's just a single idea. Maybe there's other ideas. Maybe there's other smarter things that could be done. And also, of course, thanks to these interns, they were really awesome. And without them, this project wouldn't have been possible. I believe, yeah, that's the end. Okay, yeah, thank you.